function g of x is defined on the interval 0, 8, like so, based on the values in the table, where is the function increasing? Now, the function increasing just means that if you have a picture, it's going to go up and to the right. It has nothing to do with concavity. So we only care about where this function is increasing. So it goes from -4, -3, -2, and then stops. Then all of a sudden goes down. So there's an increase right there. Then from here to here, it decreases some more. Now we go from -6 to -3. It's increasing, and then stops again. So here's our intervals of increase. So from 0 to 2, boom, and from 4 to 6, boom, 1 and 3, 1 and 3, A is my guy. What is the average rate of change on the interval from 13 to 25 seconds? Well, you're 13 and you're 25. The average rate of change formula is f of b minus f of a over b minus a. That's the slope formula, boys and girls. So we'll call you A, we'll call you B, which makes you f of A and f of B. And now it's just a matter of plugging stuff in. 30 minus 76, f of B minus f of A, over B, 25, minus A, 13. What was that, -46 over 12? Let's see, you could divide the top and the bottom by 2. And that's just about it. So, nothing fancy here, just good old plugging stuff in, and you're done. Easy peasy. Selected values of a function f are shown in the table below. Okay, hello table. Suppose n is equal to the average rate of change in f on the interval 0, 4. So let's quick do that. Okay. N is equal to the average rate of change. So n is going to equal f of b minus f of a. So you would be like my f of b, you would be like my f of a over b minus a. So f of b is 0, minus f of a is -8, so I have a double negative there, over b, which is 4, minus a, which is 0. So that's going to be double -8 over 4, and it's 2. Okay, got n down. P is equal to the average rate of change of f over interval 610. It's funny, NP are my initials and 610 is my area code. So you would be my new f of a, and you would be my new f of b, and you would be my new a, and you would be my new b. So P would equal f of b, which is -40, minus f of a, which is -16, over b, which is 8, minus a, which is 6. -40, double negative becomes a positive, so we got -24 over 2, and that becomes -12. So n was 2, p was -12. Which of these could be a true statement based on the values of n and p? The function f could be a linear function because n equals p. Well, that's not even close. The function f of x could be a linear function. It's not linear. I know it's not linear because the rates of change are different, so I'm not even going to bother. The function f of x could be quadratic because n equals p, but n doesn't equal p, so no. The function f of x could be quadratic because n does not equal p, which is true. So if it's quadratic, the rate of change is always changing. This is asking for rate of change, and the rate of change is changing or has changed. So yes, this could be quadratic because the rate of change is not the same. Is there a global maximum or minimum for the function? Now, global maximum or minimum is just fancy talk for absolute, which means is there a spot on a graph where you can't go any higher or can't go any lower? Well, what I have is an 8th degree polynomial with a positive leading coefficient. So I don't know exactly what I have, but if it's an even degree and it's a positive leading coefficient, At one point, it's going to start like that and end like that. So at one point, like no matter what we have in between, we are going to bottom out somewhere. It could bottom out at 2 spots, but that doesn't really matter. We are going to have at least a global minimum for a problem like that. So that's basically our answer. The question was not where it happens, not when it happens, but do you have a global maximum or a global minimum? Well, in this case, we're going to have a global minimum just based off of this leading coefficient right there. F of x equals x squared minus 5x plus 4. When is my function less than or equal to 0? Well, this is what I have. I have a positive leading coefficient quadratic, so I know my graph is going to look like this. What I don't know is what my zeros are. So let's factor this guy out and find out what my zeros are. So two numbers that add up to -5 and multiply out to 4 are going to be -4 and -1, which makes my zeros 4 and 1. So I'm going to make myself a sign chart. Okay, magic happens at 1 and magic happens at 4. I know this picture, when drawn, is going to go through the x-axis at 1 and 4, and I know since this is a positive leading coefficient quadratic, that is going to go like that. Just pretend it's a perfectly straight line, and it's supposed to go where it's supposed to go. Good, no one will ever notice. Now that's what my picture looks like. My picture, when drawn on a coordinate plane, will look like this, go through 1, bottom out somewhere, and go through 4. What do I need to know? I need to know when f of x is less than or equal to 0, which means where is my graph below and touching the x-axis? It touches the x-axis at 1 and including 1, and the reason, again, why we include 1 is we want it to equal 0. So include 1. It stays below the x-axis, negative. Between 1 and 4, hits the x-axis again at 4, which means it's a 0, and that's it. So whenever you're asked to do these, you factor out, you find your zeros, you draw a general picture, you answer the question, bada bing. Describe the end behavior in limit notation. Well, what I have here is I have a -3x to the 6th, and that is my leading term. So two things that we're going to look at. I'm not going to draw this picture as accurately as humanly possible. This is what I know. This is an x to the 6th power. An x to the 6th power is an even degree polynomial, which means the way it opens up is the way it ends. But since this is a -3x to the 6th, that means it starts from the bottom, like Drake, and then goes up, makes a few bumps, and ends at the bottom. So I don't know what's happening in the middle here, but who cares? All I know is it looks like that or something like that. That's how it ends. We only care about the end behavior. So the way we write out the left side of the end behavior is as we move to the left, this is going downward. So another way of saying move to the left in limit notation is the limit as x approaches -infinity. Now we're talking about g of x, so I'll say of g of x. Since we are going downward, as x moves to the left, we're going downward, we are going to say that my limit as x approaches -infinity of g of x is also -infinity because we're going down. Just like Fall Out Boy. Remember that song? Very old song. Now, as I move to the right, I'm going to word that as the limit as x approaches +infinity. And what's happening to g of x as I do that? Well, I'm also going down, which means I'm also heading towards -infinity. All right, so the trick is you look at your leading term. You look at if it's positive or negative, and you look at if it's even or odd. And since this is even, negative leading coefficient, we go down, both of them are -infinity. Funzo. Okay, so in this make-believe problem, we have ourselves what looks to be a table on a graphing calculator, and we answer a bunch of questions. Now, let's take a good visual of what we have. All right, t is very small, and it works its way up. H of t is very big and works its way down. So without knowing everything, this is basically the picture that we have. Okay, there's some curves probably somewhere built in there, but all I know is on the very left to the very right, we go up, down, and that pattern doesn't seem to stop. So find h of 999. Well, it's right there. Negative 478. Don't overthink it. Find the limit as t approaches infinity. As t gets larger, that number is getting smaller, 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 faster, so we can assume that number is just going to keep dropping down to negative infinity, like so. As t increases without bound, the h of t, now increases without bound is just fancy talk for the limit as t approaches infinity of h of t, which we already know what's going to happen. But what's going to happen as it increases without bound, the h of t, I don't know how it wants us to word this, but I stole this problem from the internet, so I'm just going to word it the way I want. We'll say decreases, because we already know it's negative infinity, so we'll just say it decreases and continue to use words. Find the y-intercept. The y-intercept exists where x is 0, or in this case t, and when t is 0, you're at 32. Find the limit as t approaches negative infinity. That means as we move to the left, my picture is moving up. The number is getting much, much, much larger as t gets much, much, much smaller. So we will say positive infinity. And as t decreases without bound, which is the same thing as what E is saying, the h of t increases. And that's the way we will word it. So we can say consistent with C. And there you go. Look at this graph of f. It's definitely some type of, rational function. We have ourselves what looks to be a slant asymptote. We have ourselves what looks to be a vertical asymptote, probably around 1, 2, 3, 4. So negative 4 is what I should have said. So dashed line through negative 4 if I knew how to draw a straight line. We should be able to answer some questions here. We got a hole right there. First and foremost, domain. The only number that you're not allowed to plug in appears to be negative 4 because that's where a vertical asymptote exists. So negative infinity to negative 4, union negative 4 to infinity appears to be my domain. My hole seems to live right there, and that's at 1, 2, 3, 4, 5, 6, 7. So my hole exists at x equals 7. My 0 is any number that crosses the x-axis that's not a hole. Okay, I have two of them, one at negative 2 and one at positive 2. So my zeros exist at negative 2, positive 2. My vertical asymptote is that vertical line that cuts through negative 4. So that's the equation x equals negative 4. My horizontal asymptote is a straight line where everything levels out. Well, there is no straight line where everything levels out. It looks like we have a slant asymptote. And since we have a slant asymptote, we have no horizontal asymptote. My y-intercept is supposed to be an estimate, so I'm going to estimate that at, I don't know, a half, negative a half, I mean. So we'll say negative a half. We're estimating. We're not being perfect. That's for Jesus to do. But look at that. We answered a bunch of problems. Good job, everybody. All right, section 1.9, poorly drawn, is asking us to find, in this case, the limit notation of a vertical asymptote. Now, we have two vertical asymptotes, one happening here and one happening here. Those are my vertical asymptotes. I'm going to try to draw the dashed line. I usually fail miserably. That's all right. And that's all right. So the way we write out the limit notation of my vertical asymptotes and what it means is we're looking at what's happening as the vertical asymptote, or as I approach the vertical asymptote from the left and from the right. So let's focus on this one at negative 2 first. If I want to describe or write out the limit as my x approaches negative 2 from the left, I'm going to put that little negative up there. That means from the left. I don't have a function, so I'm not going to call it f of x or anything like that. I'll just say equals. Now, what this looks like is I'm approaching my vertical asymptote. I'm approaching negative 2 from the left. And as I go towards negative 2, I shoot down here. And since I'm pointing downward, that means I'm shooting down towards negative infinity. Now, I'm going to do the same thing, but I'm going to approach negative 2 from the right side, so I put that little plus sign up here. As I'm going to -2 from the right side, I'm going to ignore all this stuff. I'm heading towards -2, and as I go towards -2 from the right, I'm shooting upward, which is positive infinity. That takes us to the limit as x approaches our next vertical asymptote, which is at 3. So the limit as x approaches regular 3 from the left has me traveling from the left, ignore this, traveling from the left, and as I go to 3, I shoot up, which goes towards regular infinity. The limit as x approaches +3 from the right side has me traveling from the right, and as I go towards +3, I also shoot upwards to positive infinity. Now, this happens because of even multiplicity. I don't know if we're going to run into that problem in a later problem, but yeah, that's why that happens when that happens, but that didn't happen here because I just gave you the pretty little graph. Thanks for watching. Hope this helps. We are given a table of values here, and we know it's a rational function, and we're supposed to answer questions about limits as numbers approach -3 from the left and from the right, and then it rewords those. So we're given this table, and this table gives us values that kind of look like you would plug it into a TI-84 plus and hit table, and something like this happens, but it's different. What it's telling us right here is -3 seems to be really important, and then we take something really close to it, and get even closer, get even closer, get even closer. Similarly, on the other side of -3, we take -2.9, which is really close to -3, and we get even closer and even closer and even closer. So what we want to do is we kind of want to draw ourselves like a fake graph centering around -3 and using the numbers -3.1 and -2.9, like that. Also, it looks like the magic number here is like 4.2-ish, and then something is undefined. We'll deal with that when we deal with that, but I'll put 4.2 here. Now, let's focus on the left of this -3. At -3.1, I'm at 14.13, and then I get bigger, a little bit, but bigger, like $14.13 some cents, $14.15, $14.18-ish cents, $14.19-ish cents. What's happening is we start a little bit below 4.2, and this is 4.2, not -4.2. This is just me saying it's regular 4.2. See, look, fixed. So I'm starting out a little bit under 4.2, and then I hit undefined. Now, why would I hit undefined at -3? Because it's a vertical asymptote. So what's going to happen is I'm going to hover a little bit below 4.2, get bigger, 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 and then shoot up like that. Okay, that's what happens at asymptotes. Similarly, over here on the other side, at -2.9, I'm at 4.37, which is somewhere above 4.2, and then I get smaller, smaller, smaller. Okay, but what's most important is I hit undefined again. So moving from the right to the left, my values get smaller. So at 2.9, I'm at like 4.3. And as I get closer, I'm at like 4.30 and then 4.2-ish. So what's going to happen is this is going to happen. Okay. So now based off of this picture, we can answer some of these questions. The limit as x approaches -3 from the left means I'm traveling from the left and I'm moving up as I go towards -3. So my answer is going to be positive infinity. My limit as t approaches -3, positive means from the right. So I'm coming from the right, I'm approaching -3, and then I shoot downward, which means it's negative infinity. So as t approaches -3 from the left, the d of t goes towards infinity. So we'll use a word like increases so we don't repeat ourselves. Increases. And as t approaches -3 from the right, which is what this is saying, the d of t decreases because it's going towards negative infinity. So kind of a very bizarre problem, but nothing is impossible. Hope this helps. Divide this guy using long division and synthetic division. All right, so whenever you're being asked to do long division or synthetic division with polynomials, you need to make sure things are in descending order or standard form and that you're not missing anything in between. X squared, regular x, and 4. Good, perfect. X and regular number, good, perfect. So I'm not missing anything in between. Let's do long division over here. Okay, the way you set up long division is you put the denominator on the left, you put the numerator right here, and then your quotient is going to be what you get up here. So let me write this out. Now, the first step is basically like regular old long division. You take your factor and you multiply, or you say to yourself, x times what gets me x squared? Well, x times x gets me x squared, so I'm going to put x right there. Just like regular long division, you take that x and multiply it to your factor. X times x plus 6 is going to be x squared. X times 6 is going to be plus 6x. You take this green line and you subtract the entire line, which means you flip the signs of both of these. So this will always disappear. And now I have negative 9x minus 6x, which is negative 15x. Drop down the plus 4 and repeat the process. Okay, negative x, or regular x rather, times what gets me negative 15x. X times negative 15 gets me negative 15x. Take that negative 15 and multiply it to everything here. Negative 15 times x is negative 15x. Negative 15 times 6 is negative 90. Subtract this entire row, which means you flip the signs of everything, and this gives me a remainder of 94. Now, I will write out now that this is a remainder of 94, and in a minute I'll explain what that means, but we're not there quite yet. Let's do synthetic division. A lot of people prefer synthetic division because it's faster. So synthetic division is going to look a little something like this. You make a little box up here, you make a little box down here. In this box, you put the number that makes your denominator equal to 0. The denominator equal to 0 would have negative 6 make that happen. So I'm going to put negative 6 in here. Up here, I'm going to put the coefficients of everything up here in the numerator. So invisible 1, negative 9, and 4. So that's your synthetic division setup. Step number 1 with synthetic division is you drop down the first term. Take that number and multiply it to your root here. 1 times negative 6 is negative 6 and write it there. Add these two and get negative 15. Repeat. Negative 15 times negative 6 is 90. Add these two and you get 94. Now what's that 94? That's your remainder, just like we had over here. Now, the way you answer these problems to its completion, if you're being asked to just do division and nothing else about like slant asymptotes, that'll be my next video. What you do is you say, all right, my answer is x minus 15. However, if you have a remainder, the way you write out your remainder is you say plus that number, 94, over your factor x plus 6. And that'll be my answer to this guy. Okay, and what that looks like here is you put 94 over x plus 6, you leave negative 15 on its own, you attach x to 1. But there you have it, long division, synthetic division, tons and tons and tons of fun. F of x equals 2x squared minus 3x plus 1. F of x minus 2 plus 5 happens to be g of x, find g of x. So in order for me to find g of x, what I have to do is I have to take f of x, which is this guy right here, and replace every x with x minus 2. So f of x minus 2 means I write out f of x, but replace every x with x minus 2. So 2 times x minus 2 squared minus 3 times x minus 2 plus 1. And then at the very end here, we still have plus 5. So g of x is f of x minus 2 plus 5. This is a perfect square trinomial. So you become x squared minus 4x plus 4 U can be distributed. So negative 3x plus 6. You guys can combine to make 6. U can be distributed, so that can be 2x squared minus 8x plus 8 minus 3x drops down. These guys can combine to make 12. And then U are alone, 2x squared. Negative 8x and negative 3x make negative 11x. And 8 plus 12 makes 20. So that's what g of x is. Isn't that nice? Sure is. It sure is nice. Answered it for you. A patient receives a dose of painkiller. The function p of t equals, in the numerator, 2t squared plus 10t, denominator t cubed plus 1, and it models the amount of painkiller in the bloodstream over time. T is hours. P is painkiller in milligrams. It's a calculator problem. It's a calculator problem. We're going to need it with this ugliness. So part 1 is going to be find P of 2. Part 2 is going to be finding the average rate of change. And part 3, also known as C, is going to be the maximum amount of painkiller. So let's whip out a calculator, do each part at a time, see what we end up with. All right, so first things first, we have to plug in this formula. Whenever you're plugging in a formula, two things in this case, t's or x's, that's fine. But thing number 2, since we have a fraction, let's make sure we wrap the entire numerator in parentheses so that we have 2x squared plus 10x all in one parentheses. Then we can divide t cubed, so x, we'll do math 3 for cubes faster, plus 1. All right, hitting graph. There you have it. Now, what we're going to do is part number 1 is asking us to find P of 2 and explain your solution in context. Two ways that we could do this. The easiest way to find P of 2 is by hitting second table and going down to 2. That's our P of 2, which is 3.11111. So let's go back to our slides and write out 3.11111. All right, so we ended up with 3.111 going on forever. And what that means in context means after 2 hours, we had 3.111 milligrams of painkiller in our bloodstream. So 3.111 milligrams of painkiller in the bloodstream at 2 hours. And so we'll write it out that way because we don't have space to write everything else. B is asking us to find the average rate of change from t equals 1 to t equals 2. Let's write out B here because I, again, stole this stuff from the internet and I didn't give myself a whole lot of space. The average rate of change formula is f of B minus f of A over B minus A. So in this case, what we're going to do is we're going to find out what f of B is, which we already did. If it's 1 to 2, that would be like an A and that would be like a B. So we know what f of B is. We know what f of 2 is. Minus f of 1, we don't know what that is. All over 2 minus 1. So let's run to our calculator and figure that out. Part 2 of this is asking us to find the average rate of change between the intervals 1 and 2. So I'm going to go back to my table. Second graph goes back to my table. I'm going to use the values for P of 2, which I already found out to be 3.11111, and P of 1, which was 6. So I'm going to use 6 and 3.11111 in that order. So while I'm here, I might as well do it because the numbers are friendly enough. Parentheses 3.111 minus 6 all over 2 minus 1. So divided by 2 minus 1, I think I can handle the 2 minus 1 part, but I'm typing it out anyway because it takes time. And we get negative 2.889. So let's go back to our slides and figure out what that means in the real world. All right, so the calculator reminded us that that was 3.111 minus our new value, which was 6, all over 2 minus 1, which ended up being 1. Typing that out in our calculator was negative 2.889. 9. Now, what that means is at this moment between hours 1 and 2, we lost 2.889, lost because it's negative, milligrams of painkillers. So that's the value that we get. And again, that means in the real world that we went from 6 to 3.111 milligrams of painkiller in our bloodstream. And so, that's the rate per the 1 hour that we had. Now, C is asking us to find the maximum amount of painkiller, and so we're going to use our calculator to use the maximum value and find out what we get. Our last thing we have to do is find the maximum amount of painkiller. So let's go back to our graph, and we have this picture where when time equals 0, and by the way, we don't care about negative time because that doesn't exist in the real world. It shoots up and then it comes back down. All right, so our max lives right around here somewhere. The way we can calculate our maximum is we go to second, calc, and use the maximum value 4. So obviously it comes up and it goes back down and it never, reappears. So I'll use 0 as a left bound. I'll use, I don't care, 6 as a right bound, enter. And so it's going to tell me my maximum is going to live between 0 and 6, which looks to be the case. So hitting enter one more time tells us that a maximum occurs at 8.51 hours. And that maximum is going to be 6.161, I think, was milligrams. So let's go back to our slides and write all that stuff out. So part C, the maximum value ended up being 6.161 milligrams, and that happened at 0.851 hours. So calculator problem, lots of fun. I hope you'd enjoyed it as much as I did. A linear regression model is used to construct a function model P that models the price over the given years. If T equals 1 corresponds to 2012, T equals 4 corresponds to 2015, and this pattern continues, which of the following defines the function P? So I'm awful at these, so I have to write this out. 2012 is 1. Which makes 2015 4, which makes 2018 7, which makes 2019 8, which makes 2020 9, which makes 2022 11. Never forget. All right, so let's throw that in our calculator and see what happens. Stat, edit. Let's type in those awful numbers. The numbers that we wrote before were 1, 4, 7, 8, 9, 11. Forget. Then we end up with the other numbers, which were 7.96. Was it 96? Yep. 8.17, 8.97, 911 again, never forget, 916, and 1012. 10, 12. This problem is asking us to find linear regression. So let's go to stat. Let's go to calc. Let's hit 4. I don't need this equation again, so I'll just hit enter, not need to store it. And I end up with 0.206x plus 7.540 or 7.541, which appears to be A according to our problem. Okay, it's A. Thanks for watching. Bye. Consider the arithmetic sequence A of n with the following terms. You have A sub 5 equals that. You have A sub 11. So the fifth term is 12.4. The 11th term is 34. Determine the first term. So usually when I see problems like this, arithmetic sequences, I write out the formula for the arithmetic sequence and see what I have. And the problem is I don't have the first term. And what's worse is I don't have the common difference. But I can find the common difference because the 11th term is 34. If I subtract out 12.4, I know that that skips 11 minus 5 stuff. And if you're looking at that saying, isn't that the average rate of change? It is, because the average rate of change is going to give me the common difference between two numbers. So I'm using the average rate of change formula to find the common difference. So 34 minus 12.4 is going to be, what is that, 21, 9 plus 10, 0.6 over 6. So that is 3 because 6 goes into 18 3 times. That gives you 3.6 left over, 3.6. So that is my common difference. My common difference is 3.6. Now I have enough information where I can do the rest of this. So let's rewrite the equation over here. I want to find the first term. I already know that the 11th term is 34. So let's just say let's do the 11th term. Okay, a sub 11. And the reason why I kind of want to do that is because I will do 11 minus 1, which is 10. Life is going to be a lot easier. So if I use the 11th term was 34 minus a sub 1, which is what I don't know what I'm trying to find, plus the fact that we use the 11th term minus 1 times the common difference, which we just found. 34 is a sub 1, I don't know, plus 10 times 36, 3.6. I'm looking at that like something's not right. 3.6. That's going to be 34 equals a sub 1 plus 36. There we go. Freudian slip. Subtract 36 from both sides. Subtract 36 from both sides. And your first term is negative 2. So as long as you don't make stupid errors, you'll be all right. Gustavo wanted to increase traffic to his website by buying ads on other websites. 1 month after buying his first ad, he had 4,200 visits to his website. 3 months after buying his first ad, he had 6,048 visits to his website. If the traffic to his website increases by a constant proportion every month, write a geometric sequence to represent this increase. Now, if you're looking at that guy right there, you should be thinking, all right, well, I'm allowed to use a calculator. That guy looks an awful lot like this because they basically are the same. This is exponential regression. So what we're going to do is we are going to run to our calculators and we're going to use exponential regression to write an equation. And then once we have that equation written out, we'll just fix those letters and stuff like that. All right, so Gustavo wants to make a geometric sequence, which is the same as exponential regression. So what I'm going to do is I'm going to go to Stat. I'm going to go to Edit, and I'm going to type in my 2 data points. 1 month matches up with 4,200. Okay. Bada bing. Month 3 is 6,048. Like so. Now, all I care about is the equation, so I'm just going to quit out of this. I'm going to go to Stat. And again, you're not looking for geometric sequences. Geometric sequences and exponential regression are the same exact thing. So if I hit exponential regression, go down to calculate, it gives me y equals 3,500 times 1.2 to the x, which, not using the exact letters, matches up with b. All right, so the equation that we came up with is y equals 3,500 times 1.2 to the x. So all we really have to do is, replace y with g of n and n with x. And we're not going to get that one, but we're actually going to get that one, which is b. I don't know why I circled the stuff in a. I just wanted to show that, g of n and regular n. But b is going to be our guy. The limit as x approaches negative infinity of 1/3 times 1.2. Oh, okay, so this is what we have. We have ourselves exponential growth. So we have ourselves something in the form a times b to the x. Now, anything that is in that form where I have growth here, where b is greater than 1, is always going to look like this on a coordinate plane. Let me get a different color, give or take. Now, what I don't see here is I'm not adding or subtracting anything. So I'm going to 0 as I move to the left and positive infinity as I move to the right. What do they want? They want me to move to the left. So as I move to the left, I flatten out at 0. Nothing crazy there. Just because that's a 1/3 doesn't mean anything. The only thing that would change this is if I add or subtract a number here. That would shift it up or shift it down. But shifting it left or right makes absolutely no difference because I would still end up at 0 all the way to the left. The function f is given by f of x equals 3 to the x minus 3 as the exponent, and its graph is shown above. So, first things first. Okay, this is the same thing as 3 to the x, but since you have x minus 3 inside the parentheses, you move to the right 3. Okay, move to the right 3. Is that at all what I want to do? No. Which of the following is the equivalent form? So that's not at all what I want to do. So I just have a picture for no reason whatsoever. What they want me to do is they want me to turn 3 to the x minus 3 into one of these guys. Now, whenever you get two things being added together as an exponent, it's because you multiplied terms of the same base. So now that I don't need this anymore, let me back it up a little bit. Let me go in reverse. If I gave you a problem like 3 to the x times 3 to the 4th, you would say these are terms of the same base. Let's add the exponents 3 to the x plus 4. What must these be in order to get something like this? Well, that 4, if that was, I thought I had it. If that was a negative 3, would have me adding the exponents, and x plus negative 3 is x minus 3. So I can rewrite this as 3 to the x times 3 to the negative 3rd. Now, is that an option? No, 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 and no. Now, what I do know is 3 to the negative 3rd can be written out as 1 over 3 to the 3rd. So I have 3 to the x times 1 over 3 to the 3rd. Is that an option? No. So let's take it one step further. 1 over 3 to the 3rd can be written as 1 over 3 times 3, 9 times 3, 27. So is 3 to the x times 1 over 27 an option? Sure is. So what's the point of this picture right here? Nothing. Nothing at all. Tricked you. An exponential function of the form y equals a times b to the x passes through the points 529 and 1588. Find the initial value a of the exponential function. So I'm just going to run to my calculator and do exponential regression using these two guys as my two data points. So this one is just a good old-fashioned exponential regression problem. Hit stat, hit edit. My 2 points are 529, enter, enter. And then my other guy is 1588, enter, enter. Quit out of it. I don't need to use this equation later. I just need to find the equation. So let's go to stat. Let's go to 0, which is my exponential regression. And it gives me the equation once I go to calculate. Y equals 16.64 blah, blah, blah times blah, blah, blah to the blah, blah, blah. But the only blah, blah, blah I care about is that 16.6477, which rounds up to 648. The answer is C. So according to this, the A value that I got was 16.648, which is C. Pretty easy. The table above shows the height of the ball with regard to time, and it bounces up and down. What type of model should be used to calculate the height of a ball as it is a function of time? Basically, if you're expecting, if you drop a ball and it bounces, and in this case, it bounces a little bit more, and then peaks out a little bit less, a little bit less, a little bit less. It's definitely not linear. Okay, since it goes up and then down, it's definitely not exponential, because exponential only looks like this, where it just goes up. It's definitely not logarithmic, because logarithmic goes like that, which means, it bounces up. It still increases, but slows down its increase, whereas exponential increases, and increases at a faster rate. This guy bounces up and down. So without doing any real math, I know it's quadratic because it goes up and then down. The graphs of f of x, boom, and g of x, boom, are showed in the figure above. Evaluate f of g of 3. Now, this can be written as f of g of 3. So what I'm going to do is I'm going to find out what g of 3 is, and then once I have a number, I can find f of whatever that is. So according to this, g of 3, there's 3, g of 3 appears to be negative 3. So g of 3 is negative 3. So f of g of 3 is the same as f of negative 3, like so. So let's go to f. Let's go to negative 3. F of negative 3 appears to be 4. D is my answer. Ooh, wasn't that nice? The graph of the function f of x is shown in this figure. On which of the following intervals is f inverse defined as f inverse greater than f of x? All right, well, let's do this. I have 1, 2, 3, 4 points that I care about. Okay, let's write out those 4 points as regular f. I might have to erase that, but that's okay. What do we call that? We call that f. So I have negative 5, negative 3. Great. Okay, these are xy values. Negative 5, negative 3, that gross-looking 3, negative 3. Negative 1, that's nice. I have 4, 0, that's nice. And then I have, that looks like 6, 4. Now, why did I write this out? Well, I'm going to try to graph its inverse. And really, I want to use these points as a foundation because trying to graph it without the points is just going to be a nightmare for me. Remember, when you have the inverse, you flip-flop the x and the y values. Okay, so now you have negative 3, negative 5. Now you have negative 1, so nothing there changed. Now you have 0, 4, and now you have 4, 6. Okay. So let's graph this out to the best of our ability. Negative 3, negative 5 is going to live right there. Negative 1 didn't change. 0, 4 lives right there. And 4, 6 lives right there. So, you know, this is not going to look pretty. Nothing I do here ever does. But what you're looking for is you're looking for a reflection along this y equals x axis, which I kind of see it. I see it. Now, what am I supposed to do here? I want to find where the inverse is greater than the regular f of x. Well, the inverse is green. And it looks like the moment we hit that negative 1, my green line is above this black line here, which means at this moment, f of x's value, f inverse of x's value, the green line is higher than the f function. So after negative 1 and all the way to regular 4, because it stops at 4, after negative 1 to 4 appears to be where my f inverse is bigger than my f. So between negative 1 and including negative 1, I guess, maybe not including negative 1. So I'll keep that as a parentheses. In between negative 1 and regular 4 is going to be C. Not to be confused with It's Going to Be Me, a song by NSYNC, made famous by Justin Timberlake. Hope this helps. Write the equation below in its equivalent exponential form. All right, well, exponential form looks like this. B to the x equals y. I could take something that looks like b to the x equals y and rewrite that as log base b of y equals x. So I'm given the log form. What I don't see here is I don't see a base. And when I don't see a base, it's invisible 10. So my base is invisible 10. My y is that c right there. And my 14 is going to be x. So now when I take this guy and make it look like u, I could say my base, which was invisible 10, to the 14th power is going to equal c, which is u. So 10 times 10 times 10 a bunch of times. 1 with 14 zeros attached. That's like my bank account. Hopefully after you guys keep watching these videos, that'll be true. That actually won't be true. That's a lot of money. Like and subscribe, though, please. The pH of a substance is a measure of the acidity of a substance on a scale from 0 to 14 grade. The pH of a substance is calculated by that familiar-looking formula, pH equals negative log X, where X is the hydrogen ion concentration of a substance in moles per liter. Which of the following best describes the relationship between the hydrogen ion concentration of a substance and the pH of a substance? All right. A substance with a pH of 4 has 10 times the hydrogen ion concentration of a substance with a pH of 3. I don't know. A substance with a pH of 4 has 1/10 the hydrogen ion concentration as a substance with a pH of... So basically what I really need to do is I need to turn this into, like it wants me to find 10 times. I need to turn this into its exponential counterpart. So pH equals negative log invisible base 10 of X. And what I'm going to do is I'm going to multiply both sides, so now it looks like this. I'm going to multiply both sides by -1, so now I have that. I'm going to turn that into its exponential friend. So what that looks like is 10 to the negative pH is going to equal X. And X stood for the ion concentration, or the hydrogen ion concentration, the hic for all of you people who live down south. Sorry if I offended you. A substance with a pH of 4 has 10 times the hydrogen ion concentration. All right, so if the pH is 4, all right, that means if the pH is 4, that's 10 to the negative 4th. 10 to the negative 4th is the same as 1 over 10 to the 4th, which is 1 over 10,000. 1, 2, 3. Okay. Pretty small. If it has a hydrogen concentration of 3, or a pH of 3 rather, having it backwards, pH of 3 means I'm going to have 10 to the negative 3rd, which is 1 over 10 to the regular 3rd, which is 1 over 1,000. This purple one is 10 times more than the green one. Is that what they wanted? So the 3 is 10 times more than the 4. They said the 4 is 10 times more than the 3. No. The substance with the pH of 4 is 1/10. Yep. The 4th is 1/10, because if I were to multiply U by 1/10, that works because it's smaller. That's smaller. So it's B. Has nothing to do with adding more to it or subtracting 10 to it. It has to do with taking 1/10 of it. Very interesting problem. Didn't like it at all. Not at all. Hated it, actually. Hated it a lot. A logarithmic function, f of x equals 2 log, no base, I wonder what that means, x plus h plus k, has that limit where f of x is going to hit negative infinity as you approach -3 from the right. Oh, it also passes through the point -2, 4. I have a calculator here. I don't think I'm going to use it. In fact, I'm not going to. So even though it's a calculator, I'm not going to worry about it. This is what I know. Whenever I have to deal with graphing logs and it looks like that, I'm going to compare it to its actual form, f of x equals a log base b of x plus h plus k. It's actually x minus h. Pardon me, pardon me, pardon me, me. Pardon me, pardon me, me. That does change things here. Now, what do I have? A is 2, and that gives me a vertical stretch here. Not really going to affect base off of the 2 numbers that I see here. We'll get to that in a second. Okay, log base b, again, not going to really affect anything. Log base 10, not going to affect anything. Don't worry about it. This is what I have to worry about, this statement right here. Okay, if the limit as x approaches -3 from the right is my infinity, and this guy is positive, that tells me when graphed, I'm going to have a vertical asymptote at -3, because this picture is going to go like that. So again, I'm coming from the right to -3 and hitting negative infinity. So that's my guy right there. Whenever I have a vertical asymptote, I know that my vertical asymptote equation is x equals h, which means h is -3. So part 1, we're done. H is -3. Now, K is always going to be where your point is 1 unit to the right of the asymptote. It just so happens that -2 and -3 are 1 unit away from each other. And since -2 is 1 unit to the right of -3, that tells me that K is 4. So if I were to write out this equation in full, and maybe this is where the calculator would come in handy, even though I'm not going to use it, I would graph 2 log base 10. And remember, the regular log in your calculator is log base 10. So you can just plug this straight into your calculator. Of x, what did I say h was? -3. So x, in this case, if h is -3, this is going to be +3. Plus k. K is going to be 4. I would plug this right into my calculator and make sure that it goes through the point -2, 4. Now, I made a little tiny mistake here. I'm going to cross that out because they're giving me this version of the formula, which I don't like. I'm not used to that. I'm used to this version of the formula that I created. So in my case, we are going to say that the h that they want is going to be +3. So that's kind of annoying. And the k that they want is still going to be 4. But again, the reason why the calculator here might be useful is if you were to graph this guy right here into a graphing calculator and see and double check like your table, because it would go through -2, 4. Just make sure it goes through -2, 4 on your table, and you'll be in good shape. Let x and y be positive constants. Which of the following is not equivalent to log base 3 of x plus 3 plus 2 log base 3 of x minus 1 minus log base 3 of x plus 2? All of these have the same base, which means they combine. Now, you always want to combine things that are adding first. When adding 2 logs of this, oh, I didn't even notice that. This has a 2 living out in front. I take it back. This is the first thing you want to do. If you have a coefficient attached to a log, you're allowed to take that number and set it as the exponent to the stuff inside the log. So that middle guy becomes log base 3 of x minus 1 squared. Log base 3 of x plus 3 doesn't change, so we'll write that out. X plus 3, that's still there. Minus log base 3 of x plus 2 is still there. Now we can deal with these Christmas guys that are combining through addition. When you add 2 logs of the same base, you multiply the insides. So this guy becomes log base 3, and let me add these brackets, of x plus 3, x minus 1 squared. And then on top of that, we're subtracting log base 3 of x plus 2. Always take care of the addition stuff first. Now what we have is we have the subtraction guy that's just lingering out. When you subtract 2 logs of the same base, you divide the insides. So this whole thing is now going to become log base 3 of that guy, x plus 3 times the quantity x minus 1 squared, all over that guy, x plus 2. Now to find out which one of these is not this. Well, we have our answer already. It's A. In none of these, like, I'm looking at these and you're saying, okay, I see what they want. This guy is a mirror image. These guys are exactly the same. I can rewrite out x minus 1 squared as x minus 1 times x minus 1. So B is good. C is the same. And if you look at D, you see the x plus 3. And if you're thinking, oh, wait a minute, x minus 1 times itself, x minus 1, foils out to x minus 2, x plus 1, this is eventually the same. In none of these cases do I have a coefficient of 2 lingering out here. So A is going to be my answer because A is the guy that's not the same. Isn't that fun? Logs. What are all the values for x for which log base 3 of x minus 8 is less than or equal to 3? All right. First things first. I am not allowed to plug in specific numbers. And I know that whatever this is, if I have a log base b of x minus h, whatever h is becomes my vertical asymptote. So I am not allowed to plug in anything that is 8 or below. If I plug in 8, I'm not even allowed to plug in 8. So my domain here, that's supposed to be an m, my domain is going to be 8 to infinity, not including 8. If I were to plug in 7, this would be 7 minus 8 is negative 1. You're not allowed to do that. So that's the first thing that I need to keep in mind. I have a domain restriction right there. I'm going to keep that off to the side. Okay, now this is what I'm going to do. I care about when x is living inside the log, and I need to find when x is living inside the log. I hate the way that looks. So let me rewrite this out. Log base 3 of x minus 8 is less than or equal to 3. I want to get rid of that log so I can have x no longer living inside of a log. So what I'm going to do is I'm going to take the 3 to the of both sides. 3 to the log base 3 cancels out. X minus 8 drops down. That's going to be less than or equal to 3 to the third, which is 27. If I add 8, and if I add 8, cross u out, I end up with x is less than or equal to 35. So if my domain says that 8 is the smallest number that I'm allowed to plug in, and this guy here says that 35, including 35, is the largest number that I can plug in, then my x values are going to be everything in between 8, not including 8, and 35, but including 35. So no calculator needed on this one. Bye. The function g of x equals a times f of x results from dilating f of x equals log base 2 of x by a factor of a. All right, so g of x is just a times f of x, and f of x is that. Why don't I just write that out? Why do I have to complicate things? G of x is going to equal a times log base 2 of x. Use the table of values below to determine the value of a. Well, I'm not good at finding logs off the top of my head, so why don't I do this? Why don't I change this into its other form, its exponential form? I'm going to just turn g of x into g because that'll make my life easier. And then I'll plop a right there, okay, because I'm allowed to use that formula that says if I have a living in front of a log, I can make it an exponent. So now I have log base 2 of x, okay? If I take 2 to the, of x to the a. That was a close one. If I take 2 to the of both sides, right, that crosses out, and now I have 2 to the g power, or, g of x, is going to equal x to the a power. Now that I have this information, I'm going to use this table to determine what a is. So let me just pick u. Let me pick u. Okay, x is 4. Okay, so 4. A is what I'm looking for. 2 is 2. And g to the x is 10. Well, that's very unpleasant. I don't know what 2 to the 10 is, but you know what I can do? I can rewrite 4 as 2 squared. Multiply these guys, and you have 2 to the 10 equals 2 to the 2a. If 2 to the 10 equals 2 to the 2a, then 10 equals 2a. Try saying that really fast. So if 10 is 2a, divide both sides by 2, and a is 5. Function f is an exponential function. Which of the following graphs could represent f in a semi-log plot where the vertical axis is logarithmically scaled? All right, so an exponential function is basically something that follows a curve. The goal of a semi-log plot, and as you can see by these pictures, you kind of have like this space, and then that space tightens up, tightens up, tightens up. The goal of a semi-log plot is to make an exponential function or a logarithmic function appear linear. 1 does that because that appears linear to me. 2 doesn't because that appears not linear to me. And 3 does that because that appears linear to me. So the answer for this one is going to be 1 and 3, because the goal of a semi-log plot is to make exponential functions or logarithmic functions appear linear, and those are the guys that do just that. F is a periodic function. One period of the graph f is shown below. On the interval -10 to 10, and including those numbers, how many values of x satisfy the equation f of x equals 1? Well, here's issue number 1 and issue number 2. Issue number 1 is I only give you 3 spaces of this thing that's supposed to stretch out between -10 and 10. Issue number 2 is I don't have -10 to 10. So this is how I'm going to handle this. I know that this repeats its behavior every 1, 2, 3 spaces. So what's going to happen is f of x equals 1 exists here and here. And all of these repeat every 3 spaces. So where are we right now? We're at 3 right now for that one. So let's do different colors. Let's ignore the fact that I drew that there. Okay, let's bring back the blue. And so what's going to happen is I'm going to hit this spot every 3 spaces. So 3 plus 3 at 6, this is going to happen again. At 9, that's going to happen again. Now at 12, it's going to happen again, but I don't care. Let's go in reverse. At 0, it's going to happen again. At -3, it's going to happen again. At -6, it's going to happen again. At -9, it's going to happen again. At -12, it's going to happen again, but I don't care about -12. Okay, so also we are at 1, 2, 3, 4, 4.5 right there at the green spot. So f of x is equal to 1 at around 4.5, which means at 7.5 it'll happen again, which means at 10.5 it will happen again, but I don't care about 10.5. Let's get rid of that comma to keep consistent. Now let's go backwards. At 1.5 it'll happen again. -3 is going to be -1.5, it'll happen again. -4.5, it'll happen again. -7.5, it'll happen again. -10.5, it'll happen again. But that's all that we care about because we're not going beyond -10. So we have 1, 2, 3, 4, 5, 6, 7 instances where this part hits 1, and we have 1, 2, 3, 4, 5, 6 instances where this part hits 1. 7 plus 6 is lucky 13. So kind of a bizarre, unique problem, but the purpose is to demonstrate how periodic functions repeat, and it just makes you think outside the box a little bit. An angle with a measure of 5.7 pi would be equivalent to which of the following angle measurements? Well, if I'm given something in radians and I'm talking about an angle, what I do know is if I have a coordinate plane and I were to try to measure an angle, I would start over here at 0 and spin my way around. Now, every time I spin around in this direction, I complete a complete circle, which is the same as 2 pi. So what I need to do is I need to take that 5.7 pi and either add or subtract 2 pi until I hit one of these guys to see which one of these guys is the same. And if you're wondering, oh, well, hold on, isn't 5.7 pi and like 3.7 pi different? No, if I were to take 5.7 pi, which looks something like this, right, give or take. If I were to take 5.7 pi and subtract 2 pi from it, I get the same thing because I'm circling 2 pi. So I'm going to take that, and all of these numbers are smaller. I'm going to take 5.7 pi and subtract 2 pi until I get one of these guys here. So if I take 2 pi away from that, I get 3.7 pi. Okay? None of those. If I take 2 pi from that, I get 1.7 pi. So I passed u, so none of those. If I subtract 2 pi from this, I get negative 0.3 pi. So that one. But if I just want to be safe and stuff like that, I could take subtract another one and get negative 2.3 pi, which passes u, and do it again, which passes u. So there you go. There you have it. You're allowed to take anything and add or subtract 2 pi, and it'll end up being the same exact angle measurement. Fun stuff. An angle alpha corresponds to a point on the unit circle root 3 over 2, 1/2. What are the values of sine alpha and cos alpha? All right, well, we have this point right here. Let's label u, x, and y. If this is the unit circle, we can assume that the radius is 1. Okay, so in precalculus, we refer to sine alpha, no longer thinking SOHCAHTOA thoughts. We just know that this is going to be y over r. So in this case, using this point right here and the fact that r is 1, sine alpha is going to be 1/2 over 1, which means sine alpha is just going to be 1/2. Cos alpha is going to be x over r. So in this case, x is root 3 over 2. R is 1. So cos alpha is just root 3 over 2. Okay? Very basic stuff. Just remember, sine alpha is y over r, cos alpha is x over r, and if you needed it, tan alpha would be y over x, but we don't need tan alpha, just those guys. Thanks for watching. For the function f of theta equals cos theta, what are all values of the domain when f of theta equals 1? All right, so let's take a look at what cos theta looks like. We're now in section 3-4, so we know what sine and cosine look like from a graphical standpoint. So cosine starts up here at 1, bottoms out at -1. Okay, starts out here, it crosses at 1/2 pi, it bottoms out at pi, at 1.5 pi, it comes back up, and it peaks out at 2 pi. Okay, so those are the sweet spots. Starts up here, bottoms out there, hits the x-axis, peaks out at 2 pi, repeat. Now, I care when f of theta equals 1. Now, 1's right here. F of theta is going to equal 1 an infinite amount of times because it always peaks out at 1. Look at that perfectly straight line to represent that. So basically, at 0, it's 1. And at 2 pi, and then at 4 pi, and then at 6 pi. So how do I represent that? Okay, well, this is going to happen every 2 pi's. Well, what I'll say is this is going to equal 1 when theta equals 2k basketball, 2k pi. Now, what is k? K is all integers. Any integer for all k is you know what? Let me not use calculus language. I was going to say I was going to use the integer thing for all integers k. So if k is 1, 2 pi makes sense. If k is 0, 0 makes sense. If k is -1, that makes sense because it's -2 pi. So any integer k, theta, is going to be a possible answer because it's periodic and it repeats itself. So there you go. What is the frequency of g of theta equals cos theta? Well, whenever you have a sinusoidal function, the number in front of theta, in front of your angle, is technically considered the frequency. So the frequency is 1. Thanks for watching. Write the equation of the cosine curve. All right, before we try to come up with an equation, let's try to remember what cosine looks like. Cosine, give or take, is going to be starting at 1 and then coming down and repeating itself at 2 pi. what I need to do is I need to take a look at this and see how this differs from the regular cosine curve. What I see right off the bat is, first things first, I am not centered at the x-axis. I am moved down, looks like one whole unit. Also, things are kind of like squeezed a little bit, and my period is different. So I'm looking at three things that are off. Okay, so let's take a look at thing number one. Thing number one is my amplitude. That's probably the easiest thing to look at. My amplitude is going to be the highest point minus the lowest point, and then take that guy and divide that by 2. Now, my highest point appears to be at -1/2, and then my lowest point appears to be at -1.5. Which means the difference between -1/2 and -1.5 is 1 full unit. Does that mean my amplitude is 1? No. My amplitude is going to be half of that. So half of 1, let me get out my calculator, is a half. So that's going to be my amplitude. That's thing number one that I need to focus on. Thing number two, probably the other easy thing, quote unquote easy thing, is to figure out where my midline is. What my midline does is that gives me the vertical shift. Now, my midline is literally me taking a line and cutting my cosine in half. Now, that appears to happen right around here. Now, what my midline does is my midline tells me where my vertical shift is. Okay, so my vertical shift, and I'll write this out as VS just because I don't have all the space in the world, has me moving down 1. Okay, or I'll write this out as a vertical shift of -1. How will that affect my cosine function? Well, after I do all of my cosine stuff and the things attached to cosine, I'm just going to subtract 1 to it, and that takes the whole thing and moves it down 1. Okay, so that's going to be my vertical shift. Last thing is, since my cosine kind of started out, my peak was where it should be, I don't have a phase shift or a horizontal shift, so thank God I don't have to worry about that. However, what I do have to worry about is my period. Now, my graph is supposed to repeat every half or every 2 pi. That doesn't happen here. My period is every 1 pi. So if your period is every pi, period is also given to you by figuring out what your frequency is. Now, frequency, when written out, is the number attached to x. The way you find out what your frequency is you take your period and you do, and I like to call, by the way, I like to call my frequency B. It's going to be 2 pi divided by the period. The period is pi. So this is going to be 2 pi divided by pi. Pi's cancel out. So my B, or my frequency, is just going to be 2. Okay? So let's write all of this out now that we know what we know. Okay? Y equals, my amplitude is going to be the number in front of cosine attached to cosine, and my amplitude was a half. Cosine is cosine. My number attached to x is going to be my period. So, I'm sorry, my frequency. So my frequency gives me 2x. And then since this is bumped down to 1 unit, since the midline is at -1, I'm subtracting 1 from this whole thing right here. So that's my cos function. When we deal with phase shifts and horizontal shifts, things change and it makes things a whole lot messier, but thankfully we didn't have to deal with that here. Just the other 3, dunzo. A population of rabbits in a certain forest can be modeled using a sinusoidal function of time. A minimum population of 500 rabbits occurs at month 3. The next maximum population of 540 rabbits occurs at month 9. What is the period of the sinusoidal model? Okay, so it starts out by saying, okay, It starts out by saying at 3, you have 500 rabbits. Okay, 500 rabbits. And then it says the next maximum, which is key, happens at 9. And that maximum is going to be 540 rabbits. So 540 right there. So if this is sinusoidal, you're going to look like this, which means this is half of a period. So to complete the process, if it takes 6 to get half of a period, that means the next half of the period, or to complete the period, you're going to add 6 to 9, which is 15. So this guy can come back down and complete its cycle at 500 again. Okay, so what is the period of the sinusoidal model? Well, 15 minus 3 gives you a period of 12. 12 months. A year. For those of you who don't know what 12 months is. In a right triangle, the measure of one acute angle is pi over 6 radians. What is the value of the tangent of that angle? Well, I know it mentions right triangle, but I'm going to view this from the viewpoint of a unit circle, because if you remember, the unit circle gives you parts of a right triangle. There we are. And so the angle that it gives me is pi over 6. Pi over 6 is like right here. Now, I can view this as a right triangle if I call u y and if I call this part x. But most importantly, the angle is pi over 6. Now, if you remember from the unit circle is split up into dot, 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 dot. This is 0, and this is pi, which means pi over 6 is that first dot that I have right there. Now, that gives me the coordinate root 3 over 2, 1/2. Now, tangent of theta is given to us by y over x. I know that because tangent is sine over cosine, and if I do a little bit of simplifying, I end up with y over x. So in this case, tangent of theta is going to represent 1/2 over root 3 over 2. So tangent of pi over 6 is going to be 1/2 of root 3 over 2. Now, whenever you have a fraction divided by a fraction, multiply the top and the bottom by the reciprocal of the denominator fraction. So 2 over root 3 over 2 over root 3. That allows me to completely clear out the entire bottom. And it just so happens that these 2's cancel out as well. That leaves me with 1 over root 3. Now, you were probably taught back in the day that you should never have square roots in the denominator, so we rationalize the denominator by multiplying the top and the bottom, the numerator and the denominator, by root 3 and root 3. 1 times root 3 is root 3. Square root of 3 times the square root of 3 is the same thing as the square root of 3 squared, in which case the square and the square root cancel each other out, and we're left with the square root of 3 over regular 3. So yeah, there you go. That's the tangent of pi over 6. Fun stuff. Given that the domain of the sine function is restricted to negative pi over 2 and pi over 2, in order to define its inverse function, okay, so basically it's just reminding you, hey, by the way, sine looks like this. If you make the sounds, it makes it easier, right? And it's telling you in order for this to be a sine function, or in order for the inverse to exist, we have to cut u off at pi over 2 and negative pi over 2. Okay. Now, keep in mind, by the way, keep in mind what this is supposed to look like is its inverse is basically a mirror image that flips this sideways. Okay, in order to find essential. What is the range of arc sine x? Now, arc sine is just fancy talk for sine inverse. Don't lose sleep over it. Arc sine is fancy talk for sine inverse. Now, I'm doing a bit too much. I just wanted to show you that, hey, if I were to take this and flip it sideways, we get this weird looking thing that looks like this. Okay, that is what we get. Now, in order to define its inverse function, what is the range of arc sine? Well, the range of an inverse is the domain of the original. And it tells you right now that the domain is that. So the domain of the original is negative pi over 2 to pi over 2, which means the range of the inverse is going to be the same exact thing. All right, so kind of weird stuff going on. But yeah, there you have it. Find all solutions 1/2 times sine theta equals negative root 3 over 4. Now I have to get theta all by itself, so let's start out by getting rid of that half and multiply both sides by 2. So multiply u by 2, multiply u by 2, that crosses out. Sine theta equals 2 over 4 simplifies out to 1 over 2. So this ends up being negative root 3 over 2. And you might be like, whoa, brother. Why all that space right there? Well, the next step is to get sine all by itself, which means I have to get theta all by itself, which means I have to get rid of sine. And the way you get rid of sine is you inverse sine both sides. Like so. That crosses out, and theta now equals the inverse sine of negative root 3 over 2. So basically what this question is asking is what angle, or sine better yet, of what angle gets me negative root 3 over 2. So now we have to think unit circle thoughts. Sine in the unit circle is a y value. And I'm taking the inverse sine of a negative y value. Where is y negative on the unit circle? Well, underneath the x-axis. So sine is negative underneath the x-axis down here. Now, if I were to put dot, 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 and dot, dot, dot like so, and do all the things and try to find out where sine or y is negative root 3 over 2, well, that will happen right here. I would get 1/2. Not that that's important, negative 1/2 technically, and negative root 3 over 2, which corresponds, that's this point, by the way, which also corresponds to this point, by the way, as well. So whatever x value, negative root 3 over 2. Okay, this is pi, which means u are going to be 1/3 between pi and 2 pi, which is 4/3 pi. So let me say that, 4/3 pi, or 4 pi over 3, however you want to word it out, which means this is going to be 5 pi over 3. So theta is going to equal 4 pi over 3 and 5 pi over 3. Ooh, however, I have no interval here saying that those are going to be my only answers. So I need to find all of the solutions if 4 pi over 3 is a possible one and 5 pi over 3 is a possible one. Well, what are all of my solutions? Well, basically this point and every plus 2 pi, every plus 2 pi, or every minus 2 pi, minus 2 pi. So the way I will word this out at the very bottom is I will say theta is going to equal 4 pi over 3, but I'm going to add 2 pi a bunch of times. So I'll say plus 2k pi. What's k? K is any integer. So if k was 0, I would add 4 pi over 3. If k was 1, I would add 2 pi. Or if k was negative 1, I'd subtract 2 pi, which basically just means every time I spin around the circle. So if I do that for 4 pi over 3, and you noticed all that space over there, I'm going to have to do that with every 5 pi over 3, which means every time I spin it around the circle normally, or if I subtract 2 pi, that's going to do it too. So 5 pi over 3 plus 2k pi as well. Okay? And that'll give me all possible solutions for that equation right there. Wasn't that fun? All right, let's graph g of x equals cosecant x. Now, whenever I graph cosecant or secant or cotangent, I like to view it from the point of view of its reciprocal. So cosecant is 1 over sine x. And so what I'm going to do is I'm going to graph sine x as kind of like my guide to graph cosecant x. So what do we know about sine x? Well, regular sine x starts at 0, 0. It peaks out at 1. It bottoms out at -1. Period of 2 pi. So let's graph that out. Okay, 0, and then it peaks out here, and then it re-hits, and then it bottoms out, and then repeats. And then the reverse is also going to be true, so let's draw that out. Okay, sine. Now, this is, again, like a rough draft or a guide, if you will. Not even a rough draft, but more of a guide. Because if you saw my video on secant, what's going to happen is very similar stuff. Okay, very similar stuff. Now, what's very important that I understand here is I have a x in the denominator, which means there's going to be a point, literally, and several of them where sine of x is going to equal 0. Well, whenever sine of x equals 0, that means cosecant has a vertical asymptote. Well, that just means that sine x is 0 at these moments right here where it crosses the x-axis. So you are a vertical asymptote. You are a vertical asymptote because x equals 0. Because sine x equals 0 at these moments. So vertical asymptotes here where it crosses the x-axis, and vertical asymptote here where it crosses the x-axis. Now what I have, and again, very similar to secant, not sequent, is I'm rotating what appears to be like parabolas. Where do these parabolas start? Well, right here. Okay. Why do they start right there? Because it's following the pattern of its reciprocal. So this is basically going to look like it has a parabola here. Okay. This is going to kind of go downward. This is going to go upward. And this is going to go downward like so. Okay. So if I was a better artist, this would look a lot prettier. But I'll give myself a little pat on the back. This ain't so bad. Verify the identity cosecant squared x cosine squared x is the same as cosecant squared x minus 1. This is where I start out with the left side. I do a little math trickery to see if I can end up with something on the right side. Couple ways you could approach this. I mean, some people might look at cosecant squared x and do something with the 1 plus cotangent squared x, but I'm not going to do that because I don't think that's going to help me here. So instead what I'm going to do is I'm going to turn cosecant squared x into what its actual version is, 1 over sine squared x. Okay, that's going to be multiplied to cosine squared x. And now I have myself like a little fraction looking thing. Now what this fraction looking thing actually is cosine squared x over sine squared x. That is the same exact thing as cotangent squared x. Why? Because cos over sine is cotangent, so 2 coses over 2 sines is 2 cotangents, right? So now that I have that, I know that cotangent squared x is the same as cosecant squared x minus 1 because of the Pythagorean theorem identity, which is what I wanted to get all along. Look at that, I did it. Graph the polar coordinate 3 and then 3 pi over 4. Now, we're used to seeing what's called a rectangular coordinate, where when we see two numbers, we think, oh, well, let's go right 3 and then go up whatever 3 pi over 4 is. No. This is a polar coordinate. Polar coordinates are given to us where the first number is r. R is the magnitude. R is how far away we draw our coordinate from the 0, 0 or the pole axis. 3 pi over 4 is the degree that we go if we were to go counterclockwise starting from the positive x-axis. Basically what we've always done. So what I do is I start from 0 and I go to 3 pi over 4 which I don't have labeled, but I know 3 pi over 4 is this guy right here. And so this is the line that represents the angle 3 pi over 4. And then since 3 is the magnitude, I'm going to go 1, 2, 3 units away from 0, 0, the pole. Put a nice little dot right there, and that's it. That's my answer. That's how you graph a polar coordinate. Make a table to help draw the polar graph for r equals 4 cos 3 theta. All right, so we're making a table. This is going to be a doozy, or maybe I should say a daisy. Oh, that pun probably won't make sense for about 10 minutes. But if I remember, I'll bring that pun back and remind you why that would be so funny. So I'm going to make a table. In a previous example, what I did is I graphed the polar graph by making the actual graph of the sine or cosine function, whatever it was. Now, this is r cos 3 theta. So it's 4 cos 3 theta. So it's going to peak out at 4. And what's going to happen, since that's a 3, that means that's going to be how many times it repeats itself until it hits 2 pi. So I start up here, bottoms out, repeat, bottoms out, repeat, bottoms out, repeat at 2 pi. So as I make this table, I should expect things to repeat. Now, in the previous video, it was, I believe, some number sine theta, and when I graphed that, it was a circle. This is going to take on a different shape because of the number being multiplied to theta. And these shapes will be specific depending on the number multiplied to it. We'll talk about that at the end too. But let's tarry no further. Let's pick all of the angles that I see until I run out of space, because like I said, what's going to happen soon is things are going to start repeating. So I'll pick 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 3, pi, and then we'll see what happens if I need to make any more. All right, I'm going to plug in that theta into 4 cos 3 theta, and that'll give me an r value. All right, so if I do 4 cos 3 times 0, that's going to be 4 cos 0. We'll deal with that when we have to deal with that. 4 cos 3 times theta is going to be 4 cos 3 times pi over 6. 3 pi over 6 is pi over 2. I'll deal with that. 4 cos 3 pi over 3 is pi. 4 cos 3 pi over 2 is 3 pi over 2. 4 cos 3 times 2 pi over 3 is 6 pi over 3, which is 2 pi. Now, wait a minute. 2 pi is the same as 0. Oh, I wonder if this is where things start to repeat. I guess we'll find out. 4 cos 5 times 3 is 15. So 15 pi over 3 is 5 pi over 2. Well, hold on, that's beyond 2 pi. So this is just going to be pi over 2 if I were to subtract. So now we definitely see what's going on. That's the same as pi over 2. This next one is going to be the same as pi, because it would be 3 pi minus pi. So now we're repeating. All right, so let's do the math. Cos 0 is 1. 4 times 1 is 4. Cos pi over 2 is 0. So 4 times 0 is 0. Cos pi is negative 1. 4 times negative 1 is negative 4. Cos 3 pi over 2 is also 0. So 4 times 0 is 0. And now we repeat. So you become 4, you become 0, you become negative 4, and so on and so forth. So let's graph the points that we have right now. Okay, at 0, at angle 0, I go out to 4. At angle pi over 6, I stay at 0. At pi over 3, I go out to negative 4. Oh, I'm going the wrong way. So pi over 3 is going to be over here. 1, 2, 3, 4. Ooh, careful, careful, tricky, tricky. At pi over 2, I'm at 0. At 2 pi over 3, I'm at 1, 2, 3, 4. At 5 pi over 6, I'm at 0. 5 pi over 6. At pi, I'm at 0. At, well, hold on. So basically, if I'm repeating myself, right, this is going to just be like, all right, so what was pi? Pi, again, was -4. So you would be 0, you would be 4, you would be 0, you would be -4, you would be 0, 4. Repeat. So you're 0. You're 4, so I'm repeating my dot. You're 0. You're -4, so backwards 4, repeating my dot. All right, so basically, those are the dots that I have. Those are the dots that I see. A lot of them are just repeating. Okay, no big deal. Now what I need to do is start connecting these things. Okay, I need to start connecting these things. Since what I'm doing is when I'm starting out at 4, as I move towards pi over 6, I'm moving towards 0. So as I move towards pi over 6, I'm heading towards 0, so that happens. As I move towards pi over 3, I'm heading towards -4, so that's going to happen. As I'm moving towards pi over 2, I'm heading to 0, so that's going to happen. As I'm moving towards 2 pi over 3, I'm heading to 4, so that's going to happen. As I move towards 5 pi over 6, I'm heading to 0, so that's going to happen. And as I move towards regular pi, I head to -4, so that's going to happen. And then I repeat, and then I repeat, and then I repeat. Again, I'm at 0, and then this goes to 4. So there's no need for me to draw the same exact outline again because of repetition. So I repeat, okay? Now, what we have here is called a rose, which is what makes the daisy joke so funny. I'll pause for laughter. Okay. Now, fun fact, whenever you have number cos 3 theta, okay, or sine 3 theta for that matter, if you have sine or cosine 3 theta or 5 theta or whatever, if that number is odd, you get a rose with, if it's odd, if n is odd, you get a rose with n petals. So if you see a problem like this on a test, and it's for cos 5 theta, you can expect a rose with 5 petals. If it was sine, it would start out at a different spot. It would just kind of shift over a little bit, almost as if this was a fan moving counterclockwise just a little bit. Now, what if this was something like 4 cos even petals? If n is even, what's actually going to happen is you're going to get double the amount of petals and things a lot more symmetrical. So it would be 2n petals. Okay, so if this was 4 cos 4 theta, you can expect a picture where it's 1, 2, 3, 4, 5, 6, 7, 8 total petals. So, yeah. But this is the typical rose problem. We really rose to the occasion on that one. Oh, like and subscribe. Find the absolute value of this weird complex polar coordinate here. Absolute value is just fancy word for distance. The distance between 0, also known as the pole, and the dot that you would draw out. Well, the distance is going to be the magnitude. So the absolute value, the distance is 3. All right, thanks for watching. Have a good day. Hey.